13.8 billion years ago, there was nothing, no space, no time, no matter. Then everything began. From a point smaller than an atom, the universe exploded into existence with unimaginable power and infinite potential. This wasn't just an explosion in space. This was the explosion of space itself, expanding faster than light. In the first moments, the fundamental forces of nature separated from one unified field of pure energy. The Big Bang had begun. The universe would now expand and cool for the next 14 billion years. Hi. In the first trillionth of a trillionth of a trillionth of a second, something extraordinary happened. At the quantum scale, space-time itself resembled a foaming sea of uncertainty. Then came inflation, a period of exponential expansion that stretched the universe by a factor of 10 to the 26th power in less time than light takes to cross a proton. Space itself expanded faster than light, stretching tiny quantum ripples into cosmic proportions. The temperature plummeted from unimaginable heat to merely trillions of degrees. These quantum fluctuations, frozen into the fabric of space by inflation's end, would become the seeds of all future structures, the blueprint for every galaxy we see today. In less than a blink of an eye, the universe had grown from subatomic to the size of a grapefruit, its future architecture already encoded in these primordial density variations. 1 microsecond after the Big Bang, the universe was a seething soup of elementary particles. Quarks and gluons danced in a cosmic ballet, too hot to form stable matter. As temperatures dropped to mere billions of degrees, quarks began combining in groups of 3, forming the first protons and neutrons, the building blocks of all atomic nuclei. Matter and antimatter created and destroyed each other in brilliant flashes of pure energy. But a tiny asymmetry, 1 extra matter particle for every billion pairs, ensured our universe would be made of matter. Electrons and positrons spiraled around each other in deadly dances, annihilating on contact. The universe was opaque to light, a glowing fog of particles and radiation. By 3 minutes after the Big Bang, the first atomic nuclei formed. Protons and neutrons fused to create helium, establishing the primordial mix of elements that would fuel the first stars. For 380,000 years, light remained trapped. Photons bounced endlessly between charged particles, unable to travel more than microscopic distances in this dense plasma. As the universe cooled to 3,000 degrees Kelvin, a transformation began. Electrons slowed enough to be captured by nuclei, forming the first neutral atoms. Suddenly, light was free. For the first time since the Big Bang, photons could stream across the cosmos unimpeded, beginning journeys that continue to this day. The universe became transparent in a cosmic instant. What was once an impenetrable fog cleared, revealing vast distances for the first time in cosmic history. This first light, the cosmic microwave background, still fills the universe today. Its subtle patterns hold the memory of those density variations that would spawn all future structures. With the cosmic fireworks over, the universe plunged into darkness. No stars existed yet to illuminate the void, only vast clouds of hydrogen gas drifting in absolute blackness. For hundreds of millions of years, the cosmos remained dark and cold. Temperatures dropped to just 60 degrees above absolute zero. This was the universe's quiet age. But gravity never sleeps. Slowly, inexorably, regions with slightly more matter began pulling on their surroundings, growing denser bit by bit over cosmic time. The universe was preparing for its next act. Hydrogen gas accumulated in the densest regions, drawn by gravity into ever larger clouds, spanning millions of light years. After 200 million years of darkness, the stage was set. The cosmic dark ages were about to end in spectacular fashion, as gravity prepared to ignite the first stars. Hidden from our view, dark matter had been at work. Its invisible scaffolding formed a cosmic web of filaments, creating gravitational highways for normal matter to follow. Hydrogen gas flowed along these dark matter filaments like rivers following valleys, accelerating as it approached the dense nodes where filaments intersected. What began as tiny density differences grew into massive structures. Gas clouds collapsed from millions of light years across to mere thousands, their density increasing 1,000-fold. At the cosmic web's intersections, proto-galactic clouds began to spin. Conservation of angular momentum transformed gentle drift into rapid rotation as the clouds contracted. Temperature and pressure climbed in the hearts of these clouds. After 200 million years of patient accumulation, gravity was about to achieve its ultimate triumph. 230 million years after the Big Bang, in the core of a massive hydrogen cloud, temperature and pressure reached a critical threshold, 10 million degrees Kelvin. Then it happened. Hydrogen nuclei, crushed together by gravity's relentless grip, fused into helium. The first star was born in a brilliant flash that ended the cosmic dark ages forever. These first stars were monsters, hundreds of times more massive than our sun, burning with a fierce blue-white light. Their radiation carved bubbles of ionized gas in the surrounding darkness. Across the universe, the darkness retreated as more stars ignited. Each new stellar birth created another island of light in the cosmic ocean, another beacon in the void. The universe had rediscovered light. These population 3 stars, made of pure hydrogen and helium from the Big Bang, would burn bright and die young, but their legacy would transform the cosmos. 300 million years after the Big Bang, the first stellar nurseries bloomed. Massive stars illuminated vast nebulae, their radiation triggering waves of new star formation. Shock waves from stellar births compressed nearby gas clouds, creating a chain reaction of star formation that spread through entire regions like cosmic wildfire. Not all stars were giants. Smaller, cooler stars began forming too, red and yellow dwarfs that would burn steadily for billions of years, outliving their massive siblings. Stellar winds and radiation carved spectacular cavities in the gas clouds, sculpting pillars and caverns of glowing matter, the universe's first celestial architecture. But the largest stars were already dying. After just 2 million years, a cosmic eye blink, the most massive first-generation stars exhausted their fuel, setting the stage for a transformation. 350 million years after the Big Bang, the first massive stars reached their explosive end. Their cores collapsed, unable to sustain fusion, triggering the universe's first supernovae. In death, these stars gave the universe its greatest gift. The crushing pressures and temperatures of their final moments forged elements heavier than helium for the first time. Carbon, oxygen, silicon, iron, the elements of life and planets, were blasted into space in expanding shells of brilliantly colored gas, each element adding new hues to the cosmic palette. Across the universe, supernovae enriched the pristine hydrogen clouds with these newly forged elements. The cosmos was no longer chemically pure, but gaining the complexity needed for future worlds. Where these enriched clouds collapsed, new stars formed, second-generation stars containing traces of heavy elements. The universe had begun recycling itself, death enabling new life. 400 million years after the Big Bang, gravity began binding star clusters together. What started as isolated groups merged into larger structures, the universe's first proto-galaxies. These early galaxies formed along the cosmic web's dark matter scaffolding, appearing like pearls on invisible strings, connected by the underlying gravitational framework. Unlike modern galaxies, these were chaotic, irregular collections of young blue stars. Just a few thousand light years across, they were galactic infants compared to today's giants. The universe was building its architecture hierarchically. Small structures merging to form larger ones, proto-galaxies growing through cosmic collisions and continuous gas accretion. Gas continued streaming along the dark matter filaments, feeding these growing galaxies with fresh fuel for star formation. The first galactic ecosystems were taking shape. 500 million years after the Big Bang, a new era began. The intense ultraviolet radiation from young galaxies started transforming the universe on the grandest scales. This radiation reionized the neutral hydrogen that had filled space since the universe became transparent. Bubbles of ionized gas expanded around each galaxy like cosmic spheres of influence. Where galaxies clustered together, their ionization bubbles merged, creating vast regions of transparent space where light could once again travel freely. The universe was experiencing its second great phase transition, what astronomers call the cosmic dawn, the era when starlight began to fundamentally alter the cosmos. Across billions of light years, this reionization process accelerated. The universe was transforming from a dark, neutral medium into the transparent, ionized cosmos we inhabit today. 550 million years after the Big Bang, galaxies had become complex ecosystems. Different regions hosted different processes. Star birth here, stellar death there, recycling everywhere. First and second generation stars now coexisted. The older, metal-free stars burned blue-white, while newer stars, enriched with heavy elements, glowed with subtly different hues. The interstellar medium grew increasingly complex. Oxygen, carbon, and silicon, though still rare, enabled new chemistry. The building blocks for planets and life were accumulating. Each galaxy had become a recycling factory. Gas to stars, stars to supernovae, supernovae to enriched gas to new stars. The cycle of stellar life and death continued. In the densest, most metal-rich clouds, conditions were approaching those that would one day allow rocky planets to form. The universe was gaining the complexity needed for life. 600 million years after the Big Bang, galaxies began their dance of collision and merger. Drawn together by gravity, they approached along the cosmic web's filaments. When galaxies collided, the results were spectacular. Gas clouds smashed together, triggering intense bursts of star formation that lit up entire regions in brilliant blue. From these cosmic train wrecks emerged larger galaxies. What were once separate star systems merged into single, more massive structures spanning tens of thousands of light years. The universe was building its galaxies through cosmic cannibalism. Small galaxies merged to form medium ones. Medium galaxies combined to create giants. At the cosmic web's major intersections, true galactic giants emerged. Fed by continuous gas inflow and surrounded by swarms of smaller satellites, these would become the universe's first galaxy clusters. 750 million years after the Big Bang, the universe stood half transformed. Ionized regions expanded steadily, pushing back the remaining neutral hydrogen into ever smaller pockets. At the boundaries between ionized and neutral regions, radiation compressed gas clouds, triggering new waves of star formation. Reionization was accelerating its own completion. The pace quickened as more galaxies added their light to the cosmic effort. What had begun slowly was becoming a runaway process, transforming the universe at an ever-increasing rate. By 800 million years, the transformation was nearly complete. The universe that had been opaque for its first 380,000 years, then neutral for hundreds of millions more, was transparent once again. The cosmos glowed with the light of billions of galaxies. Reionization, the universe's final major phase transition, was ending. The stage was set for the next 13 billion years of cosmic evolution. 1 billion years after the Big Bang, the universe had transformed beyond recognition. Where once was darkness, now galaxies illuminated the cosmic web in all directions. Galaxies of all types populated the cosmos. Some remained irregular and chaotic, while others showed the first hints of the spiral and elliptical structures we see today. Massive galaxy clusters had formed at the web's major nodes, containing hundreds of galaxies bound by gravity, surrounded by halos of hot gas glowing with X-ray light. The cosmic web stretched across billions of light years, its filaments traced by galaxies like lights along cosmic highways. This vast structure emerged from quantum fluctuations in the universe's first instant. From a single point of infinite density to a vast web of galaxies, all in just 1 billion years. The universe had completed its first chapter, establishing the cosmic architecture that would shape everything to come. We are part of this story, made from stars, living in a galaxy connected to the cosmos. This is our origin. This is how it all began.